All right, this is a video on the chi-square distribution and the three types of tests that we can do with it. So the chi-square distribution is a distribution that looks like a bell curve in the middle part of it, but it's not. It's actually very skewed to the right. Its left endpoint is 0, and then it has a mound shape, and then it's very skewed to the right with its tail. It can be used for three types of hypothesis testing: the test for independence, the test for homogeneity, and a test of good fit. The test statistic, this is the Greek letter chi. So chi-squared is calculated by the sum of the observed values minus the expected values or frequencies squared, because we want to make sure that that doesn't all zero out when we add them together, divided by each of their expected values for their cells. So you have to do kind of a table method again, like we did with standard deviation. The goal is that each E has to be greater than or equal to 5 in each category. So the expected frequency to the approve, essentially, the use of the test. So in testing for independence and homogeneity, they're both kind of set up the same way. We calculate the expected frequencies, that's our E's, using the following formula for each cell of our contingency table, because everything will be presented to us in a contingency table. We do each row total times column total per cell and divide that by the sample size, and that gives us our E for that cell. We will also need degrees of freedom with chi-squared. It's different than what we used for the student's T. Our degrees of freedom when we're doing either independence or homogeneity testing is you look at the contingency table and you see how many rows did you have, -1, times how many columns did you have, -1. Okay, so that's how we get our degrees of freedom. If we're doing a test of good fit, we calculate our expected frequencies differently because we're basing it off of essentially percentages or probabilities of breakdowns for each category that we have. So E is the probability assigned to each category times the sample size of our sample, whatever that is. So that's N for us. And then degrees of freedom, since we don't have a contingency table there, it'll be just K -1, where K is the number of categories that we were presented with. Okay, so let's just jump right in and look at one of these. So I'm not going to do both independence and homogeneity. I'm going to do just one of those since they're very similar in terms of the test. The big difference comes in how you write your null and your alternate. So suppose a researcher is studying the relationship between gender and voting preference in a local election. The researcher collects survey data from 500 participants and tabulates the results in a contingency table. So notice we have 2 rows for our categories here. So that's male, female, that's our gender category. We have 3 candidates, so that's 3 columns. And notice that the individual cells represent 2 characteristics at the same time: males who voted for candidate A, males who voted for candidate B, and so on. And the second row, of course, is all the females who voted for those different candidates. We have a total for our rows. This is the total of the males, total of the females. We have totals for each of our candidates down here. And then we have our total number for the sample size. So we want to test whether gender and voting preference are independent at the 0.01 level of significance. So our first step is going to be to state that null and alternate hypothesis. So our null, H sub 0, which I'm just going to put as H0, is that gender and voting preference are independent, okay, so of each other or variables, however you want to say that, but just are independent. Now, the alternate is that they are not independent, which means we're actually looking for dependency. So gender and voting preference are not independent. Okay. Oops. All right. So when you're doing this test, it's, like I said, very similar to if we're doing homogeneity testing. We would say, if this was test for homogeneity or test for homogeneous variables, we would say that gender and voting preference are similar versus they are different or not similar to their populations. So complete the contingency table calculations and find the chi-square test statistics. So I've already got the table kind of set up for us. Remember, I'm going to show the work for just this first one, and then we can write our answers for the rest. But we do our row total times our column total for this specific cell. So notice the row total is 250, the column total is 170, and we divide that by the number of people in the sample. So that's going to be how we do all of those individually. You go row by column, and then we divide, of course, each one by 500. Now, when I went through and worked all of those out, here are the values that I got for each E. I got 85, And then for this one, I got 115. For this one, I got 50. So it's exactly what they observed. For this one, I got 85, 115, and 50. Now you'll notice that this does not always happen where each of these three are the same. That is because our row totals, we had an equal split of males and females. If this had been 240 and this one had been 260, we would have seen slightly different numbers on those lines for the E's, because this number is based off of row total by column total. And in both cases, you notice the row total and the column total end up being the same for both situations. So that's why those are matching. It does not always happen that way. All right, now once we get all of that, we're going to put it into our observed and expected frequency table. This is pretty much where we come up with the chi-squared test statistic. So remember, these cells relate back to row 1, spot 1, row 1, spot 2, row 1, spot 3, and these were the ones from row 2, okay? So we had 80. These were the actual given values of our sample: 120, 50, 90. We had 110 and 50. The expected values we just came up with using the formula for E was 85, 115, 50, 85, 115, and 50. When we subtract those, we're going to get -5, +5, 0, 5, -5, and 0. Now, if we added all those together, when we talked about in class, that would actually cancel out. So we square them. So this would become 25, because when you square a negative, it becomes a positive. 25, 0, 25, 25, and 0. Then you take that difference squared and we divide it by the E for that row. So 25 divided by 85. When I do that on my calculator, I get 0.2941. Then I have 25 divided by 115. That one comes out to about 0.2174. 0 divided by 50 is just going to be 0. 25 divided by 85, we already know that, is 0.2941. And 25 divided by the 115, again, since we had some similarities with our males and females being both split exactly 250 and 250. That's why we're getting these matching values. And then 0 divided by 50 is 0. Now you add all of these up and that gives you your chi-squared test statistic. So I got 1.023. So remember, we write that that's chi-squared. And then we need our degrees of freedom, which is the number of rows -1 times the number of columns -1. And that's from your original contingency table. So we had 2 rows and 3 columns. So 2 minus 1 and 3 minus 1, that's a 1 times a 2, or 2. Okay, so once you have your degrees of freedom and your chi-squared test statistic, we'll go to our tables. We go to the specific table we have for chi-squared. You see the little symbol there. We're going to go to the degrees of freedom row of 2, and we're looking for our value, which was a 1.023. We're trying to figure out where that falls. It looks like it falls in between this 0.211 and this 4.61. So I'm going to bring that back over to my notes. Degrees of freedom, row 2 at 0.211. And then I had 4.61. My test statistic is somewhere in between there. And those probabilities associated with those specific spots were 90% and 10%. So it's a big range. So if we think about what this really is, if you think about what chi-squared looks like, you have 0 as the start of the mound, and then it goes really skewed to the right. And if we don't know exactly where that 1.023 falls on here, but we know that wherever it falls, it's somewhere in the mound, because there's either going to be only 10% to the right of it or 90%, which means it would be on this side of that. So I always just kind of rough estimate where I think that would be. And this is the area that it's telling us when we find our p-value, the area to the right. So our p-value is between 0.10 to 0.90. So remember, it's 0.10 or larger, essentially, for the p-value. And concluding the test, we have to look at our alpha, which our alpha for this problem, if we go back up, was a 0.01. We're definitely not going to be smaller than that. We are larger than that, so that means we can't reject the null. So for this specific sample is not indicating to us that gender and voting preference are dependent of each other. So the data is not significant at the 0.01 level. There is not enough evidence to conclude that gender and voting preference are not independent, which means we're saying we can't prove that they're dependent of each other. We would assume the null, which stated that they are independent variables. Okay, and then I have a second example for chi-squared because of the goodness of fit test works just a little bit differently, especially in the calculation of the E. So a lot of times you'll get this one given to you as a percentage. Just to show you a little bit different variety this time, I give you just the direct probabilities of something happening. So a probability distribution, if you have that from a previous study, you can actually set that goodness of fit test up. So it says, suppose a die is suspected to be unfair. Remember that what we learned in probability said that a fair die has an equal probability of about 1 out of 6 for landing on each face. So landing on the 1, the 2, the 3, the 4, the 5, or the 6, they all have an equal probability of 1 out of 6 sides. So a student's going to actually do an experiment and roll a dice 120 times and record their frequencies. So this is our observed frequencies. So these are how many times did they see each side of the die. So notice it didn't come out perfect because it's an experiment. So we have 25, 20, 15, 30, 10, and 20. This is the previous distribution information, how we expect this to come out, which was I'd expect 1/6 or about 16.7%, which we don't want to use that because if you round the percent, it doesn't quite add up to 100% anymore. So I'm just keeping it in fraction form. So the expected frequency should be the same for every single one. We actually rolled 120 for our N. This is 120 times. So to get your expected frequencies when it's a goodness of fit test, you take the total sample size and you times it by the probability or percent as a decimal, if they give it to you in percent form, of your actual expected distribution, the one that was kind of the previous information. So if a die is fair, this should happen. So this gives me 20, and it's going to be the same for all of them because they're all the sample size of 120 times the 1/6 equal probability. So the question is, if we have the 0.05 level of significance, test the claim that the probability distribution for a fair die fits the distribution of our current experiment. So we're trying to see, does that current experiment actually follow what we expected? So I'm going to write that out. So our H sub 0, or just H sub 0, since I can't do the sub on that, is the current distribution of dice rolls is a good fit for the probability distribution of a fair die. That's like our population one. And then H1 would be the current distribution. So our sample that we just did of dice rolls is not a good fit for the probability distribution of a fair die, which would indicate to us that that die maybe had been tampered with, maybe it has a weight in it. It doesn't fit the same, it's too different in how the numbers are falling, essentially. So we're going to write down our observed and expected again. We already had those from the previous chart, so I'm just going to bring them down. So we had 25 times they saw 1, 20 times they saw 2, 15 times they saw 3, 30 times they got 4. So if I was betting on anything being weighted, it was weighted towards the 4, 10 for 5, and 20 for 6. And this is what you should expect, is if I roll a die 120 times and I have 6 sides, I should expect to get each of them equal amount of times. So if you add both of these columns up, you should get 120, because this is just splitting the sample by what we saw versus what the probability distribution of a fair die should have given us. We do our subtraction, so we get 5, 0, -5, 10, -10, and 0. We square each of those, so that's 25, 0, 25, 100, 100, and 0. We're going to divide each of those by the expected value for that specific category. So this one's divided by 20. So that comes out to 1.25. 0 divided by 20 is just 0. 25 divided by 20 will be another 1.25. 100 divided by 20 is going to be 5, and we get that again. So this is where our deviation is really happening. It's the 4 and the 5. And then we see 0 divided by 20 is 0. So we add that up, our chi-squared test statistic is a 12.5. I would write that as my chi-squared. My degrees of freedom, when you're doing the goodness of fit, you don't really have the contingency table set up. You just had a percentage or probability distribution, and then you had some observed data. So it's just K minus 1, where K is the number of categories. So in this case, K is the number of sides on the die. So 6 minus 1 would be 5. So that's my degrees of freedom. So we'll go to our table. So degrees of freedom, we're looking at 5 this time. And our test statistic was 12.5, which is going to fall right here between those two. So I'm going to bring that over to my paper. We have our degrees of freedom. It is for row 5. We got an 11.07 to a 12.83, and that's where 12.5 fell. And the probabilities associated with that, if we look up here, are 2.5% and 5%. So p-value then would be between 0.025 and 0.05. So 2.5% to 5% in our tail. You think about our 0 being here at the beginning, we're way out here, and there's only about 2.5 to 5% area at that point. To the right of that. So when we look at our test for significance level, we were at 0.5. So yeah, our p-value, even at its biggest, would be equal to the alpha. So p-value is less than or equal to our alpha, which was 0.05. So it either equals it or it's smaller than it. So that means we can reject the null. And so our statement would be that we're going to remember kind of accepting the alternate in that point. So the data is significant at the 5% level. There is enough evidence to conclude that, and if we look at our phrasing from the actual problem, it says that the die is, well, let's put the current distribution of the die is not a good fit for the probability distribution of a fair die. So we're pretty much saying it looks like this, there's enough evidence to say that this die is probably unfair. There's maybe some weighting going on, something to make it not fit the probability distribution of what a fair die should be. All right, that is the end for the chi-squared video.